Greetings, and now if you will kindly join me, we will follow a collective series of statements to establish a definite proposition, that is, the chain rule. The chain rule says that the derivative of the composition of functions f and g of x is equal to the derivative of x with respect to g times the derivative of g with respect to x. Alternately put in this notation, the derivative of f of g of x is equal to f prime of g of x, the derivative of f of x with respect to g of x, times g prime of x, the derivative of g of x with respect to x. So this is the beginning and the end of what our proof is going to look like. So we really don't know much besides the fact that f of x and g of x are differentiable, and perhaps that x is an element of the set of real numbers. And from this information, we are setting out to prove that the derivative of f of g of x is the derivative of f with respect to g times the derivative of g with respect to x. Again, just the chain rule. So now let's start out with the alternate definition of the derivative. So the derivative of f of g of x is equal to the limit as x approaches some value c of f of g of x minus f of g of c divided by x minus c. This is just plugging our function f of g of x into the alternate definition of the derivative with respect to x. So now, using some algebra, this is equivalent to f of g of x minus f of g of c divided by g of x minus g of c times g of x minus g of c divided by x minus c, because if you notice, the g of x minus g of c's cancel, and that leaves us with just this, which is what we had up here, which follows just from using the definition of the derivative, doesn't require any special manipulation. However, this sometimes causes a problem. Suppose we had a function like this one, x squared sine of 1 over x, that oscillates infinitely many times as we get close to 0. That means that as we're taking that for any number, you will always, for any x value you take, you will always be able to find a point on the function between that value and 0, and x equals 0, that passes through 0, which means that we have a dividing by 0 problem, leading this to be undefined. So in order to get around that problem, we have to define a new piecewise function, q, such that q of y is equal to f of y minus f of g of c divided by y minus g of c, when y is not equal to g of c, and when y is equal to g of c, we'll have a workaround and just say that q of y is the derivative of f with respect to g. So now, if we plug in g of x into that function q, we get q of g of x is equal to f of g of x minus f of g of c divided by g of x minus g of c, when y is not equal to g of c, and the derivative of f with respect to g when y is equal to g of c. In this case, we have y equals g of x. So, as you can see, q of g of x is the same as this expression over here when g of x is not equal to g of c, and otherwise we'll plug in this derivative, and we'll see later that this is completely justified. So now we make our substitution, rewriting this. And now let's think to ourselves, what is the limit as x approaches c of q of g of x? That's just the derivative of f with respect to g. Because if we go back to the definition that we have over here, we see that it's g of x is equal to this quotient over here uh, or it's equal to exactly this statement, the derivative of f with respect to g. Now, what is this statement right here? This is just using the alternate definition of the derivative with respect to g of x rather than with respect to x. So this is true. And what about this? This again is just the alternate definition of the derivative of g of x with respect to x. So again, we can say that the limit of x approaches c of g of x minus g of c divided by x minus c is equal to the derivative of x with respect to the derivative of g with respect to x. So now, if we plug this back in, we know this information over here. What we get is, so once we separate the limit out, right? This is a property of limits. You can separate multiplication to separate limits. So now we have the limit as x approaches c of q of g of x times the limit as x approaches c, g of x minus g of c divided by x minus c. Plug in the information that we have over here, and we get the derivative of f of x with respect to g of x times the derivative of g of x with respect to x. And we're done. So one thing just to make sure, that how do we know that this derivative of f with respect to g is justified here when g of x is equal to g of c? Well, here's one thing we know. When g of x is equal to g of c, this value is 0, which means the whole thing is 0 anyway, so it doesn't matter what this value is right here, and it just works nicely for our proof to make it equal to the derivative of x with respect to g. So I hope we have established, and I think we have established, the truth, or at least the validity, of the chain rule, and that's all. And now, how to recognize different types of trees from quite a long way away. The larch. The larch. The larch.